Hello everyone, welcome to this channel MLGURU. My name is Arjun Pukale. In this video we will implement multivariate linear regression using Python in Google Colab. We will build it from scratch. So first what we will do is we will input all the necessary libraries. So we will be using pandas, numpy, matplotlib, seaborn, and for feature scaling we will use one of the either of these min max scalar or standard scalar from sklearn's pre-processing. Now here I have pasted the picture of the formula for dw and db which we had discussed in the previous video lecture where we had derived this vectorized form of the gradients. You can see that video first, then you will understand these formulas. Now what we have to do is we have to write code to implement this formula. So let's create our model. We will create a class of our model. We will name our class as Multivariate Linear Regression. Now first of all we need to initialize the class. So whenever you create the object of this class, this init function gets executed. So in this init what I am giving is n. I am giving as n as input, which denotes the number of features. So remember that n denotes the number of features or number of columns, and m denotes the number of rows. So we will initialize the weights and biases as follows. First we will initialize self.w to np.random.ran and we will give the size of our array as 1, n. This we had discussed in video lecture that we have to give this weight array size of 1, n, and we will initialize b to any random scalar value. I have initialized it to 0. You can initialize it to any random value. Now the next function is pred. What this function does is, given an input x, it will give the predicted value based on the current values of this w and b. Okay, so how we can do that? We will do the matrix multiplication of x, which is our input, and w transpose n plus b. This is nothing but a formula for y hat. We have implemented using numpy's matrix multiplication, and here you can see the dimension. The dimensions of x are m, n, meaning m rows and n columns. That is what our input looks like, and the dimensions of w was 1, n. So to support this matrix multiplication we have taken the transpose of w, so that the inner dimension matches and we will get output as m, 1, means prediction for each values in m. Then the next function is to calculate loss based on the current prediction and actual prediction. So this loss function takes input as this y pred given by this function and the true values of y, and then I store m. M is nothing but the number of rows, so I can get that value by y dot shape. Y dot shape is a tuple consisting of two values, the number of rows and number of columns. So I am giving index 0 to fetch the number of rows, and then we calculate the mean squared error loss. And remember, this is not a scalar value. This contains m terms for every point in the y pred. Okay, so to get the loss as a scalar value, we have to take the sum. So we are doing np.sum over this loss. So we will get the mean squared error loss, and then the next function is the main function where we are going to implement these two formulas. So again I am storing the number of rows over here, and it takes input as x and y. X is the input and y is the true values of y, and we will be requiring these two for training. Now first I will calculate y hat, means the prediction, using this pred function. Once I get y hat, I have to implement this formula. So what is this? This is the y hat minus yi. So I will first subtract these two arrays, take the transpose, then multiply it with my input, and then divide every element in this by 1 over m, and it will result in array of 1 cross n. So the same thing we have done here. We are taking the difference of y hat and y, and then taking the transpose, and then doing the np means matrix multiplication with this term and this x, and then dividing every term by multiplying it by 1 by m, or simply dividing it by m. Then this will give me a 1 cross n matrix. Similarly, we will write db is equal to np dot sum y hat minus y times 1 by m. We are implementing this formula, and remember b, the partial derivative of loss with respect to b is not a vector, it is a scalar value, because b is a single scalar value. So if we have to update this using the derivative, so the derivative should also be a scalar value. Yeah, so this will give a scalar value, and then this function will return dw and db. Now this is our training loop. The fit function, it will take input as x, y, the number of epochs, the learning rate. So first thing what I will do is, so I want to keep the history of the weights and biases and also the loss. So after each epoch I will store the updated values of w, b and loss in some form. Okay, so for storing that, I have created this w hist and initialized it to self.w, because currently before training my weights have this particular value, right? So I have initialized this w hist by this array self.w. Similarly, I have declared this b hist for storing the bias, and I am storing it in a list where the first element is the currently initialized value of b, which is 0 before training. And I have created this empty loss array, and I have to store the initial loss before starting the training. So for that, since our loss function takes ypred as input, so first we will calculate this ypred based on the current initialized values of w and b, and then I am calculating this initial loss using this loss function, and then I am doing loss dot append initial loss. So I am storing the initial loss in this array. So now the main training loop starts here. So we will go through each epoch. For every epoch we will first calculate this dw and db using our self.grad function, which we have seen here. It returns dw and db, and then we will update the values of w and b using the gradient descent update rule, and then we calculate the predicted value based on these updated values of weight and bias, and then we calculate the loss for these updated values. Then we append this currently calculated loss in this loss array, and similarly we will be storing the updated values of w and b in w hist and b hist. So since w hist is an array, we will do np.append self.b hist, means I have to append something to this array, and what we have to append, the current values of w, and along which axis, along 0 axis. So remember in numpy this is axis 0 and this is axis 1, so we have to append vertically, right? So each row in this w hist will correspond to epoch number, right? And we will and since this b hist is a list, so we will simply do b hist dot append self dot b, which is the current value of b. And if you want to print the epoch number and training loss after each epoch, you can do this. I have currently commented it out. Now after going through this for each epoch, after the last epoch, I will come out of this training loop. I will print my final loss, which is the loss after my final update, and then I will plot my loss, which contains the loss for each epoch, and that's it. So this was our class. We have created our multivariate linear regression class, so our model is ready. Now let's see what our data is. So we will be using the same data which I had used for demonstrating the feature scaling. So I have loaded this real estate CSV in my local runtime. You can download it from this link. Again, I am going to give this link of this Google Colab notebook in the description box. So I have read it in this pandas data frame. So this is what my data set looks like. Now I don't need this first and second column, because the first column is just indexing and second one is the transaction date, which we don't need in making prediction, and the last column is the Y, which is the house price of unit area. So my X is all the we are fetching the X from this data frame using df.iloc method. I am saying that I need all the rows, I need all the columns from 2 up to the second last column. So after fetching X, this is what our X looks like. It has 5 features, so the value of n is 5. And to fetch Y, we will do df.iloc. We need all the rows and I need the last column, right? And also be careful about the shape of X and Y. We want X to be shape of m cross n, and Y should have the shape of m cross 1. So we have done it. Now let's apply the feature scaling. So we will be using standard scalar. We will create the object of that. We will fit to it our X, and then I will store the scaled value of X in this variable by sc.transform X. And let's have a look at the shape of X scaled. So we have total of this much number of rows and 5 columns. The shape is same as this X. And also we will convert, now currently Y is a data frame, so we need to convert it to numpy for performing the operations. So we convert it using this to numpy and have a look at the shape, which is the desired shape we want, which was m cross 1. Now let's instantiate our model. So I am calling this class we just created. I am creating an object named model, and I have to give it input, which is this n, which is nothing but number of features. So we can get the number of features by xScale.shape. Now you can see a xScaled is a tuple which is 414,5. This first value is the number of rows, the second value is the number of columns which we need. So I have it indexed here 1. Now we will call our fit function. My input is this xScaled. This is the true value. This is the number of epochs, and this is the learning rate. You can play with different values of number of epochs and learning rate, and then after fitting, this is what you will get, right? So we can see our model has learned. Once you see that the loss is not further decreasing, it has flattened out, so you must understand that the training is completed successfully. And now we will plot the values of weight and bias which we had stored in w hist and b hist. So this is what our output looks like. So how we plot it? So first we will create this plt.figure. We'll give appropriate figure size, and then we will loop through each of the weight, and then what we'll do is use plt.subplot. So I need a subplot with one row and the number of columns equal to the number of features, which is 5 in this case, and this extra plus 1 for bias. Okay, and this is the current value of this subplot. So initial value will be initial value of I will start from 0, but this subplot value starts from 1, right? So I am doing this I plus 1. So for each of this weight I am doing some labeling, x label, y label, and I will be plotting plt.plot model.whist. And remember what was the dimension of whist, it is the number of epochs. Now remember, it is 51 because 50 are for the number of epochs, and this plus 1 is for the initialized value before training, right? So we have 51 rows and 5 column, and each row, suppose I am currently at first row and the index of the first row is 0, which means it is epoch 0, meaning before training. Now I am at the first row, then it means this is the values of the weights after the first update. Okay, so I need all the rows and I just need the ith column, because there are 5 columns. Each column corresponds to a weight, right? W0, W1, W2, W3, W4, right? So at a time we are plotting just a single column or a single weight. So after going through all this, I have to plot the bias. So at the last value I will be plotting model.bhist, which is nothing but list. I am doing x label, y label, and I am using this plt.typeplot because it will prevent the overlapping of this labeling. And then we do plt.show, and then you will get this graph. So you can see this was the initialized value of w0, and as the number of epochs increases, it goes here and it settles down at some value over here. So all this, and look at w4, it first increases, then again it decreases to find a particular value. And our bias was initialized to 0, then it increased and finally got settled at a value somewhere around 40. So now we have created the model, we have trained our model. So let's do one thing, let's increase the learning rate, let's say to 0.8, and then again run this. Oh wait, we have to first again initialize the model, because then the weights will be again randomly initialized. Yeah, so you can see at a larger learning rate, instead of decreasing, the value of loss has increased drastically. So why this is happening, you can see this by this plot of weights. So you can see, due to larger learning rates, when we update the weights using the gradient descent update rule, since the update is proportional to our learning rate, if my learning rate is larger, it will overshoot the minima and it will go on the other side of the minima, where the loss is even much higher, meaning the gradient is even more higher, then it will oscillate, and instead of converging, it will diverge. So you can see all the weights are diverging, right? So we will again correct it. Let's keep that to 0.1. We have to again initialize the model. Yeah, so that's fine. Now let's plot the weights. Yeah. Now we have created the model. Now let's test our model on our own inputs. So for that I have created this function called prediction. I will give input as model. Now the model should be trained. Now for passing the input, first I need to create the input in desired form, which is m cross n. Now here I am just I want to make prediction on just single row, but for that the value of m will be 1. So what I need is a matrix, input matrix of size 1 cross n, where n is 5, right? So first I will create this empty list, then I will ask user first to enter the house age. This 5 things are nothing but the features. You can see a house age, distance, then the number of stores, latitude and longitude. So I am taking all these things as input from user, and I am converting it to float type. And then after taking all these 5 values, I have a list. Now I have to convert it into numpy array, so I am using np.asArray, and I am adding here an extra list to as I have said, I need input of size 1 cross n, but this does not have that 1 and in the starting, so this extra list will add that 1. Okay, it will increase the dimension. And then as you know, our model expects input which are scaled, so the one which we had fitted, yes, this one. So the standard scalar object which we had created and fitted on this x, we have to use that same standard scalar object. So this is this sc.transform this array which we had created. So I am giving it a name scaled array, and then finally I am printing the final prediction, which is given by model.pred function, and the input to it is the scaled array. And since it will be an array of size 1 cross 1, so I am using this indexing to fetch the value inside that array, right? So let's run it on this inputs. So let's enter the values: 19.5, 306.59, 924.98 and 121.53951. So it gives me the house, the price of the house per unit area as 48.97. So that's it in this video. So you have seen how easy it is to implement the multivariate linear regression model from scratch using numpy, and also you have noticed that because of this vectorized form of coding, we have achieved a very nice speed. If you would update each value of this w0, w1, w2, w3 using scalar gradient descent, that it would have taken very much time. So using this vectorized implementation, we have increased the speed, right? So that's it in this video. Thank you for watching.